Hi guys, in today's lesson we're looking at stress and strain. This is probably one of the easiest topics in engineering science N4. So stress is just the force per unit area. Okay, then strain is it's a ratio between the change in length and the original length. So basically, for us to understand this, I came up with an elastic. I hope you can see that. So what happens is that if I apply a force on this elastic, it becomes longer. So this elastic is, because of the force that I apply on it, it is undergoing stress, and at the same time it is having a strain. Strain is the change in length. So without applying a force on this elastic band, there won't be a strain. So stress on the elastic causes strain, but then we'll go into detail about how we calculate and how we differentiate those ones. So like we have said, stress is the force per unit area. You need to know what force is. Basically just the unit for force. We know the unit for force should be newtons. We're using N. The units for the area should be square meters. So stress is represented by that symbol. Is the force over the area. Force over the area, the unit area of a surface. That is our stress. The unit for stress is Pascal. You'll be using PA as the unit for stress. Pascal, force over the area. If we remember in hydraulics, N3, even hydraulics N4, this looks like just the unit for pressure, and the formula looks like the formula for pressure, which is just the force over the area. So our unit is Pascal. Basically, just make sure that your area, before you calculate, your area should be in square meters, your force should be in newtons. Otherwise, your calculations are going to be wrong. So make sure before you do any calculations, make sure you know that your force is in newtons, your area is in square meters. So now, you also need to know how to calculate for areas of basic shapes. Basic shapes, I mean, let's say they say calculate the area of a circle, which is pi r square, pi times radius square. But when you calculate for that area, make sure your radius is in meters, so that your answer is in square meters, in order for you to use it in this formula that we have here. Or you can use pi d square divided by 4. We can use that as the area of a circle. Again, your diameter should be in meters, and then when you square it, we get our answer in meters squared. So my whole point, my emphasis is that make sure your area, this area, make sure it is in square meters. Otherwise, our calculations are going to be wrong. If let's say area of a rectangle or area of a square, this is L times B. Make sure both the length and the breadth are in meters, so that our answer again is in square meters. Area of a triangle, half times the base times the height. These are just basic shapes. Probably this is grade 7 or grade 5. So, but we need to know how to calculate area of basic shapes, and also how to calculate the dimensions of shapes. In most of our questions that we might come across, they'll just give you the dimensions of the shape or the profile of the object that you're looking at. Then before you can calculate for the stress, you need to calculate the area separately. Alright, now sometimes they may not give us the dimensions, but they might give us the area already. And the trick will be that they'll give you the area in centimeters square. If let's say suppose they give you the area in centimeters square, this should be converted to meters square. Now how you convert centimeters square to meters square? What we know is that the prefix for cent the prefix for cent is times 10 to the power minus 2, but then we'll square that times 10 to the power minus 2, times 10 minus 2, then we square that. This becomes exponent minus 4, then this is square centimeters. So centimeters square is to the exponent minus 4. Same applies if we are looking at millimeter square. Millimeter square, we know milli is times 10 to the power minus 3, but when we square that to meters, it becomes times 10 minus 6 meters square. So this is what we'll be doing in case they give you your area in centimeter square or millimeter square and you have to convert. And also you can do the same way I've done. You can do the same to any other area, as long as you know the initial prefix value for whatever units is given. If it is cent, we know the prefix value is minus 2, so that cent we square it and therefore it becomes minus 4. The same thing, this was minus 3, we square this, minus 3 becomes minus 6, we multiply it by 2. So that is how you convert the area that has been given to you, and then if you do that, then it will be much easier to calculate. Strain is the change, it's a ratio between the change in length and the original length. So with that in mind, strain is a ratio. Strain is a ratio, we should always keep that in mind, which means strain does not have a unit, it's just a ratio, it is just a number. So when we come to strain will be represented by that symbol. It looks like a 3 facing the other way. Strain is a ratio between the change in length over the original length. Now all of these lengths should be of the same unit. If you're using your length in meters, then your change in length should be in meters. If you're using in centimeters, your change in length should be in centimeters. Other books or textbooks, they'll use X for the change in length, but it does not matter what symbol they use, but as long as we know it's the change in length over the original length. Now, in most cases, this will be a very, very small number. You are looking at maybe 0.000 something, a very small number. So in most cases, they will express it as an exponent to a negative power. Let's say they might say maybe 13 times 10 to the power minus 4 as just a number with no units. So strain, that is what we are looking at. There is a change in length. Remember the example I gave of the elastic band. If we have an elastic, we exert a stress on it, what we see is that the elastic becomes longer. I hope you can see that. The elastic becomes longer. That change in length, its original length without any force applied on it, is that then we have a change in length. How much length we have, how much extension we have, that is what strain is. It's just a ratio between the change in length and the original length. Otherwise, that is just strain. Strain has no units. Strain has no units, it's just a ratio. It's a unitless value. Alright, now with these two in mind, what we are saying is that we cannot have strain without stress. There is no strain without stress. There are 3 types of stresses. There is the compressive stress or compression, whereby the forces acting on an object, if this is our object, there is a force acting in that direction, there is a force acting in that direction. We are compressing this object from both sides. There is a force on that side. So there is forces on both directions. We are compressing this. This object will undergo a compressive stress. We are compressing it. But still, if this object changes in its length, then it is undergoing strain. It will undergo a strain, which is compressing. It is changing its dimensions. So strain is a measure. In other words, you can say strain is a measure of deformation or changing in the dimensions of an object. Then the other type of stress we can have an object. This is our object. The forces are pulling this object, like the example I gave of an elastic band. This type of stress is called tensile stress. It's a tensile stress or a tension. We are pulling the elastic, like I gave, we are pulling it in both directions. We are pulling it apart. We are exposing, or we are making a tension in that object. We are subjecting the object. We are subjecting this elastic to a tensile stress. All right. Then the other type of stress that we have is known as a shear stress. Okay, shear stress. The easiest way I can demonstrate a shear stress is when we have forces that are at a tangent to the object. Let's say this object is fixed on this surface. This object will not move. Then the force that is acting on it is acting at a tangent, at a surface point, whereby this object, if the force pulls in that direction, this object will deform to go in that direction. It will shear off, it will slant in that direction, but the object still does not move, but remains on the same position, but it is sheared onto another shape. So this object is being stressed. The object is being subjected to a shear stress, and still all of these ones, as long as the object moves or changes its dimensions, as long as the object changes its dimensions, then there will be a strain that will be associated to that. Okay, so as long as there is a stress, there will be a strain. We can never have a strain without a stress. And then, like I've mentioned, you need to know the three types of stress, but the unit still remains the same. Stress, the unit is Pascal. Strain, unitless. Whether it's a compressive or compression, a tensile stress, or a shear stress, we shall always have the unit in Pascal. Now, with these two combined, where we are saying we can never have a strain without a stress, we are required to know or state Hooke's law. Hooke's law states that the change in length, the strain is directly proportional to the stress. Okay, the strain, the change in length, depends on the stress. How much change in length, when we go back to our elastic, how much will, if I apply a small stress, a small force, then even the change in length will be less. But the more force, the more stress we exert on this elastic, the more the strain, the change in length, the more it becomes longer. So Hooke's law states that the strain is directly proportional to the stress for any object. For any object that is under the elastic limits. Okay, under the elastic limits. Elastic limits means elastic or elasticity. One term that you might be required to define elasticity. Elasticity or elastic limit is what this elastic is doing. When I pull it, exerting a stress on it, once I release my stress, it comes back to its original dimension. That is what elasticity is. So for any object within this elastic limit, as long as I apply a stress, even the change, the strain will be directly proportional to the stress that I've applied. How much change in length depends on the stress applied but that is only true within the elastic limits. So for example, if I continue pulling this elastic, it breaks. We have exceeded the elastic limit of that material. So once you exceed the elastic limit of a material, that material will break. You are no longer within the elastic limits, and therefore Hooke's law will not apply. So Hooke's law only applies within that limit, which is the elastic limit, where the object has not deformed. The object is still coming back to its original size. That is Hooke's law. So Hooke's law basically states the strain is directly proportional to the stress under the elastic limits of a material. And then the other thing that we'll be required to know, or what we are required to know, stress, strain, the other thing that we are required to know is the modulus of elasticity. Okay, modulus of elasticity. Modulus of elasticity is just the stress per unit strain. Okay, modulus of elasticity is the stress per unit strain. Modulus of elasticity will be represented by that capital letter E, which is your stress over your strain. Other books represent modulus of elasticity with Y over strain, but it doesn't matter what you use. Modulus of elasticity is the stress over the strain, and in this case, modulus of elasticity is how much stress is required to bring about 1 unit of a strain. Stress per unit strain. That is modulus of elasticity. How much stress is required to bring about a strain. So what we are dividing, or what we are working with, is that the unit for stress is Pascal. The unit for strain is no units, just a number. No units. So the unit for Young modulus of elasticity is Pascal. Okay, the unit for Young modulus of elasticity is Pascal. Now, with this, we are dividing a very small number. Remember what I said? That strain is a very small number, very small number in most cases though. We are dividing into a big number, and therefore in most cases you find this Young modulus of elasticity to be a very big number, and in most cases they like to represent it as gigapascal as the standard unit for Young modulus of elasticity. But as we know, giga is just a prefix. Even if we have megapascal, it's still a unit for modulus of elasticity. So with stress being equals to the force over the area, strain being equals to the change in length over the original length, if we break down these ones, that's what we are having. Young modulus of elasticity will end is equals to the force times the original length over the area times the change in length. In our formula page, they'll give us force times L over A times X for the change in length, and still we can get all our calculations as that. So now our emphasis, or my emphasis again, comes in: if you are using this, make sure your force is in newtons. Your length should be the same as your change in length. If your length was meters, your change in length should be meters. Our area is in square meters, so we can calculate for our Young modulus of elasticity, and modulus of elasticity is in Pascal. Sometimes it can be gigapascal or megapascal. That basically concludes our stress and strain. So we have our stress, we have our strain, we have our modulus of elasticity, and then we can calculate. Now, most common questions that we'll find are mind challenging questions. What we should also keep in mind is that if we have an object that has different dimensions, let's say we have an object of that sort, okay? The diameter of this object, let's assume, okay, let's assume we have an object like this. An object of different diameters, different sizes, but it is subjected to a force. With this object, the length, let's call this object A, object B. This object might be made of the same material. The stress that this object will undergo, object A, and the stress in object B will not be the same. The stress in object A is the force over the area. So you calculate using the dimensions of A, area of A, the force in this case will always be the same. The force will be the same throughout this object, that force, but the stress depends on the area. So with a thin object, a thin part, stress is the force over the area of this object, depending on how the object is. Alright, I hope it makes sense. So with the force being the same throughout, force in A is equals to force in B. The force remains the same, but the stress in A and the stress in B depends on their sizes. This thin object, the area will be less, therefore the stress will be high. For the thicker part, the area will be high, therefore the stress will be low, because the stress is inversely proportional to the area. So the thicker the object is, the less the stress. The more thin part will experience a lot of stress. Also, when we come to the strain on this part, the strain on A, you calculate your change in length for A over the original length for A, and also your strain for B, it's your change in B over the original length of B. Okay, now the reason why the strain, we are looking at strain in each part, the reason why the strain will not be the same goes back again to that elastic, and also goes back to Hooke's law, where we are saying the strain on an object depends on the stress. The strain is very proportional to the stress. So the strain on B depends on how much stress B will undergo, and as well as the strain on part A, how much it will extend by, depends on how much stress it experiences. So the strain in each part, the strain will not be the same. The strain will depend on how much stress each part undergoes. But however, what we need to emphasize or know is that the force throughout the object will remain the same, because both of these two parts are not going to be extending at the same time. So extension on A plus extension on B, that will be our total extension, how much it extends by, and that is what we'll be looking at. Otherwise, it's a very simple topic and you can be able to calculate any question that comes.